Welcome to the video lecture on one-sided limits and continuity. Let's review the definition of one-sided limits. A right-hand limit has as its notation the limit as x approaches a with this little plus sign up in the right corner. And that means that the x's that you use should only be x's slightly bigger than a from the right-hand side. A left-hand limit uses a little minus sign in that upper corner, and that means that you should only be using values of x slightly less than a or coming from the left side. And we have a theorem that said that the ordinary or two-sided limit as x approaches a of f of x exists if and only if both corresponding one-sided limits exist and are equal. In other words, the two-sided limit as x approaches a of f of x equals to L if and only if, that's what this two double-arrowed symbol means here, if and only if the right-hand limit is equal to L, and that is also what the left-hand limit is equal to. Okay? So the two-sided limit only exists if it's equal to the same value as the right-hand limit and the left-hand limit. So let's explore this a little bit more with some examples. Let's take the function f of x is equal to the square root of x minus 4. Now you should all know what the graph of that looks like. We all know that the square root of x graph is just a big slow arc starting at the origin and going to the right. Now when you have a minus 4 inside of your radical next to the x like that, recall that that means it's a horizontal shift. And horizontal shifts go backwards from what you would expect. So a minus 4, you might think to go left, but actually we're going to go right 4 units. So that means instead of starting at the origin, we're going to start over here at 4. And then we're going to do that slow arcing shape that a square root takes on. So that's what the graph looks like. And based on this graph, let's find the limit as x approaches 4 from the right-hand side. So if we're coming from the right-hand side, we're picking x as slightly bigger than 4. And that would correspond to these y values on my graph. As the car drives down the curve, it's heading towards that red dot, which is at a height of 0. So the right-hand limit does exist and is equal to 0. Now if we come from the left-hand side, we have a problem. Because in order to take a left-hand limit, you have to use x values that are strictly smaller than 4. And there are no x values or y values when we come from the left side. There are no x values that can be used that are less than 4, because then we would be taking the square root of a negative number, which doesn't exist. So that means that this left-hand limit must be d and e, because there's no graph to refer to. If the left-hand limit is d and e, that automatically forces the two-sided limit to be d and e as well. You can't have a two-sided limit if one of your partial limits, your left or your right limits, doesn't exist in the first place. Okay? Alright, let's take a look at some examples here. All of the limit theorems that we've learned, all the limit properties that we've learned still apply to one-sided limits. So if we take a look at this next example, first thing I'm going to want to do, like I should do with all limits, is plug in my x value to see what I end up with. And we're going to just plug in 2. Now if I plug in 2 into the numerator, I get 2 minus 2, which is 0. And in the denominator, I get 2 squared minus 2, which is 4 minus 2, which is 2. And 0 divided by 2 is 0. Since I got an actual limit value of 0, that means that this limit does exist, and we're done. We got our answer. Now, did it matter that I was coming from the right-hand side? No, because 2 minus x is a nice linear function, and if I come from the right or the left side of 2, I'm still going to be approaching 0. And if I come from the left or the right side of 2 for this quadratic, I'm still going to be approaching 2. So no matter which side I came from, the limit would still be 0. Let's take a look at this next example. We have the square root of x minus 2 over x minus 4, and we want to find the limit from the left side of 4. So first things first, plug in your 4 and see what you're dealing with. So we get square root of 4 minus 2, which is 2 minus 2, or 0. And on the bottom we get 4 minus 4, which is 0. And that is one of our indeterminate forms. So that's bad news. That means we don't know what the limit is. It may or may not exist, and we're going to have to be a little bit more creative in figuring out how to find what that limit is. Because this function has a square root in it, that makes it a good candidate for using a conjugate. So we're going to take this limit, this function, and we're going to multiply it by the conjugate of the numerator. I'm using the conjugate of the numerator because that's the one that had the square root in it. So the conjugate, remember, looks just like this but with the opposite sign in between. So square root of x plus 2, and I have to multiply by that on the top and the bottom so that I'm just multiplying by a fancy version of 1, which doesn't change what the limit value should be. Now when I do this, I'm going to put in those parentheses to reinforce the fact that we do need to FOIL. So if I distribute across the top, remember that your inner and your outer are going to cancel out. So negative 2 root x and positive 2 root x is just going to be a 0. So I'm not even going to write those because I know they will cancel out. What I'll be left with is square root of x times square root of x, which is just an x, and minus 2 times plus 2, which is minus 4. Now don't distribute on the bottom because you'll want to notice that if you just recopy these two denominators pushed together, one of the factors on the bottom is the same as the factor on the top. These x minus 4s are the same, so they will cancel out, and that will leave me with a simplified function 1 over square root of x plus 2. Now remember that after you do that canceling out step, that usually means you're ready to plug in. So if we plug in 4 into that denominator, square root of 4 is 2, and 2 plus 2 is 4, so the whole limit overall is going to be 1/4. Now I didn't use the fact that I was coming from the left-hand side at all in this problem, and I didn't need to because the square root of x is defined for numbers slightly smaller than 4. That's the only thing you'd have to worry about. Remember in our previous example on the last page, the reason that this limit didn't exist was because when we were looking at numbers to the left of 4, there wasn't a function at all. This function didn't start until 4 and later. And that's not the case for our square root of x up here. So the left-hand limit aspect of this problem made no difference at all. We didn't even have to worry about it. So now let's look at some examples where we will need to worry about what side we're coming from. And this next set of examples is pretty common. You'll see these in your homework, so you'll want to know how to do these. These are going to use something called the Heaviside Function. Now the original Heaviside Function, we've talked about this before, looks like absolute value of x over x. And you should know and have memorized what the graph of that looks like. It's undefined at 0, but when I use a positive value for x, I get that same number over itself, so it cancels out to a 1. So for all these positives, you're at a height of 1. When I use a negative value of x, again, the x's cancel, but on top it's positive and on the bottom it's negative, so they cancel out to a negative 1. So you get this big step going to the left at a height of negative 1. And since it was undefined at 0, we had these two open circles. Okay? So what does that have to do with this function here? Well, this function here is just a shift of this one. You have that minus 4 on the top and on the bottom, and it needs to be in both places, otherwise this wouldn't be a proper transformation. Because it's inside of that absolute value and next to that x, you're going to need to recognize that this is a horizontal shift, and because it's minus 4, we're actually going to go to the right 4 units. So this graph with the x minus 4s is actually going to look like this graph over here shifted to the right 4 units. So instead of having my open circles when x is 0, I'm going to have my open circles when x is 4. And instead of going to the right and to the left from 0, I'm going to go to the right and to the left from x equals 4. So that's what my new graph looks like. You need to have a visual of that graph in order to be able to answer this limit question. So now that we know what the graph is, we want to find the limit as I approach 4 from the left side. So that would be these x's here, which correspond to these y's down here. So we're on this bottom step down here. And what's the height of that bottom step? It's -1, which means this limit is -1 as well. Okay? Let's try that again with this next example. This time we want to take the limit as x approaches 1 from the right-hand side of the absolute value of x minus 1 over 1 minus x. So this should present a little bit of a problem because the top and the bottom expressions aren't exactly the same. However, the bottom one is just the flip of the top. So what I would recommend doing is flipping around the denominator so that it matches the numerator, but you can't just flip it around without changing something about it to make it equivalent to what it started from. And what we're really noticing is that 1 minus x and x minus 1 are opposites. So if I factor out that negative, that makes these two equivalent to each other. If I were to redistribute my negative, I'd get that minus x that I need right here, and a minus times a minus 1 gives me this plus 1. So that's why they're the same. And then one step further, I could take that negative and I could pull it all the way out front of my fraction and think of it this way. So tell me, what kinds of transformations do you see in this function here compared to my original Heaviside function? Because of the minus 1's, it's going to be shifted to the right 1 unit. And because of that negative, when you multiply your function by a negative on the outside, just like it is here, that is a reflection over the x-axis. In other words, we're just going to flip it over. So imagine what the graph of just absolute value of x minus 1 over x minus 1 would look like. It would take this Heaviside graph and move everything over 1 unit. So my open circles would be at 1, and I'd go to the right and to the left. Now if I put that minus out front, what does that do to this graph? Well, it's going to flip it over. So I'm still going to have my open circles at 1, but this piece of the graph gets flipped down, and this piece of the graph gets flipped up. So my two steps are just in the reverse directions. Now that we have our graph, we should be able to find our limit, and we want the limit as we approach 1 from the right-hand side. So here's 1. From the right-hand side would be this way, which are these y's down here, and they are all at a height of -1. So this limit is going to equal -1. Okay? Another kind of an example where one-sided limits are important to worry about would be the greatest integer function. So let's kind of quickly review what the greatest integer function looks like. By definition, it means the greatest integer that is less than or equal to this x. So if you're plugging in an actual integer, you're going to get that same integer back. But if you're plugging in a decimal, you're going to be getting back the integer that is just less than that decimal. So for example, if I used a half, 1/2 is between 0 and 1. So the number that, the greatest integer that is less than a half would be this 0. If I plugged in -3.75, that is between -4 and -3. So the greatest integer that is less than -3.75 would be the -4. And what that does is it gives us a graph that is just a bunch of steps. You have a solid circle on the left endpoint and an open circle on the right endpoint. These little steps have a width of 1 because they're going over by each integer. So as I get to 1, I have an open circle at the bottom and I hop up to a height of 1. When I get to 2, I hop up to a height of 2, and so forth. And then on the left here, they continue in this sort of diagonal direction. Okay, so that's what the greatest integer graph looks like. You need to have that memorized. So based on that graph, I want to approach 0 from the left-hand side, which would be slightly less than 0, which means I'm down here on this step, which is at a height of -1, so that means this limit must be -1. Okay? Now we're going to take the greatest integer function of x plus 2. So here's your transformations at work again. What transformation is it when you have a plus 2 inside of your function next to your x? It's a horizontal shift, and remember you go backwards from what you might expect. So plus 2 means we're actually going to go left 2 units. So here's how I think about it. Normally, my first step would start at the origin and go to 1. I need to take this whole step and I need to move it 2 spots to the left. So my graph is going to look something like this. Instead of starting at the origin, if I go 2 to the left, I'm going to start at -2 and I'm going to have a width of 1. Once I know where that first step is, then I know where all the other ones have to be because they just follow this diagonal. You jump down 1 height each time you go. So here's my graph. Once I know what my graph looks like, then I can evaluate my limit. I want to approach 1 from the right-hand side. So here's 1. From the right-hand side would be over here, which corresponds to which little piece of my graph? My graph is slightly crooked here, but what you need to see is we're actually, this little step here should line up more with that 1. I was a little bit sloppy in my drawing, but that means I'm actually on this step up here. Approaching, when I let x be 1, this is going towards 3. So I'm up here at a height of 3. So this limit is equal to 3. Okay? So be on the lookout for these Heaviside functions and these greatest integer functions. You'll have to do some of those with these one-sided limits. Let's try one more example with a greatest integer function in it. This time I want the limit as I approach 2 from the right-hand side of 2x minus the greatest integer function of x. Now, because this is sort of like 2 totally different kinds of functions, I'm going to split this limit up into 2 different limits using my limit properties. The limit of a difference is the difference of the limits. So let me break this up into the limit of just the 2x minus the limit of just the greatest integer function of x. Now I'm going to do each one separately and then subtract the answers. Now 2x is just a nice linear function, so it doesn't have any of those troublesome worries that we have to think about when we're talking about one-sided limits. Your answer to this limit, because it's such a nice function, is going to be whatever you would get if you were to plug in 2. So 2 times 2 is just 4. The greatest integer function, on the other hand, is one of these yuckier functions to deal with because it's a step function. So this one you will need to take the time to draw it out, just a normal greatest integer function, and then visualize from the graph what your answer is going to be. And we want the limit as I approach 2 from the right-hand side. So here's 2 from the right-hand side would mean I'm on this step, which is at a height of 2. So this limit goes to 2, therefore the difference is 4 minus 2, or 2 as well. Okay? Now one more kind of function that is going to cause us to have to pause a little bit when we're doing our one-sided limits are going to be piecewise functions. These are functions that tend to have issues with a left and a right-hand limit. So let's take a look at this function right here. It's piecewise because when x's are less than 1, you're supposed to be on this line, 3x minus 1, and when x is greater than 1, you're supposed to be on this parabola, x squared. Now for this one only, I'm going to draw the graph, but usually I am able to do these without even having to take the time to draw the picture. But I just want to review with you quickly how to do this. So 1 is sort of the key point. To the left of 1 going this way, we want to be on this line, and to the right of 1 going this way, we want to be on our parabola. So we need to get a graph that's going to show those 2 pieces. So first thing I'm going to do is I'm going to see what this line wants to be when x is 1. So if I plug in 1 for x, 3 minus 1 would be 2. So this wants to be at a height of 2, but since there's no equal bar included over here, I have to use an open circle. Now to draw a line I need 2 points, so let me pick another x value so that I can draw this line correctly, and I'm going to want to make sure I pick an x that's smaller than 1 because that's the only x's I'm supposed to use. So let's pick 0. 0 minus 1 would be -1, so that means this line goes through that point as well. Remember, we're starting at this open circle and we're going to the left of 1, so we have to go down to draw that line. We don't want to go past 1 and go to the right at all. So that's what that first piece of the graph looks like. Now let's do the same thing for x squared. If x was 1, this wants to be 1 squared, or 1. But because 1 is not included, I need an open circle at 1, 1. So that's my starting point. Now I want to pick an x bigger than 1, say 2. 2 squared is 4, so this wants to be up here. And we know that this is quadratic, so it should have a nice curve to it. And there is what my graph is going to look like. Okay? So you can visually see that there's obviously an issue at 1. Coming from the left side, we're up here headed towards this open circle. And coming from the right side, we're down here headed towards this open circle, and they obviously don't match. So we have this jump going on. We have to jump down from the line down to the quadratic. So there's probably not going to be a limit there because the left and the right hand sides are different. So let's verify that algebraically. So if we want to find the limit as I approach 1 from the left, here's what you should show as your proof. First of all, you need to tell me what part of the function, which rule up here applies if we're coming from 1 on the left side. That means we're strictly less than 1, so that means we should be using this line. So this is really going to be the limit as I approach 1 from the left-hand side of 3x minus 1. And this is a nice function, so its one-sided limit is going to be exactly what you would expect if you were to just plug in 1, and that's 3 minus 1, or 2. So we have our left-hand limit is equal to 2. Now let's do the right-hand limit. If we're coming from the right side of 1, we're supposed to be using x's that are bigger than 1, so that means we should be on the x squared function. So I want to use that rule. So x from the right-hand side of 1 of x squared is going to be, again, plugging in, because this is a nice polynomial, I'm going to get 1 squared, or just 1. So the right-hand limit is equal to 1. So what do you think that says about the two-sided limit? Well, if the left-hand limit is 2, which is different than the right-hand limit, which was 1, then the two-sided limit must be d and e. And that's because the left-hand limit does not equal to the right-hand limit. That was that theorem that we had to have true. So the problem with these piecewise functions is quite often, not always, but quite often, you will have a jump in your graph between these two pieces. And so this breaking point right here is kind of the most important point that you have to worry about potential places where there might be issues. Let's try another example. This one I'm not going to take the time to graph. I'm just going to jump right in and find my limits algebraically. So if we want the limit as I approach 2 from the left-hand side, that means less than 2, so that means I need to use x squared for my rule. So this would be the limit as I approach 2 from the left-hand side of x squared. And if I plug in 2, 2 squared is 4. Now if we come from the right-hand side of 2, we're bigger than 2, so we want to use the rule 3x minus 2. So this is going to be the limit as I approach 2 from the right-hand side of 3x minus 2, and when I plug in 2, that gives me 3 times 2, which is 6. Whoops. 6 minus 2 is 4. So the left-hand limit was equal to 4, and so was the right-hand limit. So what does that say about the two-sided limit? Well, if the left and the right-hand limits are equal, then that's the value of what the two-sided limit is. So this is 4 because the left-hand and the right-hand limits were both 4 as well. All right, Now what we're going to move into is sort of a similar topic called continuity. The formal definition of something being continuous involves several different pieces. So we're going to take a look at some of the qualities that make a function continuous or what make a function not continuous. We say that a function is continuous at x equals to c if it has no holes, jumps, or gaps at c. One sort of straightforward or sort of easy way to think about continuity is to imagine putting your pencil down on a piece of paper. If you are able to draw the entire graph without ever having to lift up your pencil once, then that means you are a continuous function. If you have to lift up your pencil because there's a hole in the graph, or a jump in the graph, or an asymptote in the graph, then that means you have a discontinuity. So let's look at some common examples of discontinuities. This first graph has a hole right here at C, and that is called a discontinuity. And the reason why it's called a discontinuity is because what's happening right here is that the function at C doesn't have a value. That's why we have a hole there. So the way we say that is f of c, the function evaluated at c, is not defined. And that's what leads us to having our hole. This is called a discontinuity at c, and more specifically, it is called a removable discontinuity, because you could easily fix the discontinuity by just filling in that little circle, and then there wouldn't be a hole anymore. So we say that it's a removable discontinuity if you have a hole. Okay, so holes are discontinuities, and specifically they're called removable. Let's take a look at another common type of discontinuity, and that would be this case of a jump. The reason that this is a discontinuity is because the limit from the left side, it's going up towards that solid dot, but the limit from the right side of C is going down towards this open circle, and those two heights do not match. So formally what's happening here is the limit, as I approach C from both sides of this function, does not exist. And in this particular example, that's because of a jump. Another way that this might possibly not exist is because of an asymptote, if these limits were going to infinity. Okay? If you have a jump or an asymptote, that is called a non-removable discontinuity. There's no way to easily fix this discontinuity, because in order for these two to match up, you'd have to change this whole curve to move it up so that it lines up and doesn't have a jump. Same thing with an asymptote. Okay? And then one last example here. Notice what's going on here. First of all, does this function have a value at C? Yes, that's what this black dot right here means. This is the value of the function at C. So that is defined. That's not the issue. Does this function have a limit at C? Well, if we come from the left side and we come from the right side, those two cars do want to crash. So there is a limit. So the limit does exist. The problem is that this limit wants to be way up here, but the function is defined way down here. So these two things are not equal, and that's the problem. So the limit not only has to exist, but it has to equal to the value of the function at C. So you're going to see this sort of problem occurring when you have a graph that has a hole with a separate point, one of these black dots that's kind of just floating around up or below the graph. This is considered a removable discontinuity because we could easily fix the problem by just redefining this point to fill that hole right here, and then we wouldn't have a hole in our graph at all. So removable discontinuities are the ones with holes. Non-removable discontinuities are either jumps or asymptotes. So let's formalize these three different things that we just came up with. These are the three conditions that need to exist in order for a function to be continuous at a point C. First of all, the function has to be defined at C. So there has to be a black dot on your graph. If there's just an open circle with no dot anywhere, then that means f of c is not defined. Secondly, the limit has to exist. You can't have a jump, you can't have an asymptote. So there has to be a limit. And then thirdly, these two things have to be equal. So not only does the limit have to exist, it has to equal to what the function equals at C. So if these three things happen, then you are continuous at a point C. And we really like functions that are continuous because they are very nice and smooth and they don't have any troubling behaviors. They don't have anything wrong with them like holes, jumps, gaps, asymptotes, things like that. So continuous functions are what we would consider nice functions to deal with. Now we say that a function is continuous on an open interval if it is continuous at each point in the interval. If the function is continuous on the entire real line, then we say that it is everywhere continuous. So let's look at this graph right here. Where would this function be continuous? Well, one of the things I answer first before I decide where it's continuous is I first decide where is it discontinuous. So let's look for the discontinuities. In this graph, imagine putting your pencil down and trying to trace out the graph without ever having to lift your pencil. If you do have to lift your pencil, that's a discontinuity. So as I come down here, I have to lift up my pencil to jump over that asymptote. So there is a discontinuity at -1. And that would be non-removable. Then if I continue along, I get to this open circle and then I have to jump down here at 1. So there's also a discontinuity at 1, and that's because of that jump. And then I can continue to trace. There's a sharp corner here, but I can still continue to trace. Then I come to this hole at 3, have to jump up, fill in that black dot, and then come back down again. So there's another discontinuity at 3, and that would be your hole. So we have 3 discontinuities. So where would it be continuous? Everywhere except those 3 values. So I'm going to write this as a set of intervals. It's continuous from -infinity up until that asymptote at 1, and then from 1 to that jump, -1 was where the asymptote was, so -infinity up to -1, then from -1 up to where that jump was, which was at +1, and then from that jump up to that hole at 3, and then from 3 on to infinity. Notice that I used parentheses around all of my endpoints because if I used a bracket, that means I'm including that point as being continuous, and I don't want to include any of these endpoints because they were all discontinuities. We say that a function is continuous on a closed interval if it's continuous at every point inside of the interval, and the limit from the right is equal to the right endpoint f of a, and the limit from the left is equal to the left endpoint b, f of b. So there are 2 classifications of a point of discontinuity on a function. There are removable discontinuities and non-removable. Remember, the removable ones have limits that do exist. These are just the ones that have a hole in the graph or possibly a hole with a separate point. But the limit does exist. The ones that are non-removable are the ones that have limits that do not exist. And that might be due to a jump in your graph so that your left and your right hand limits don't match, or an asymptote. So let's look at these examples here and decide what kind they are. So this is kind of like one of our step functions, our greatest integer function here with a little twist on the end, so it's more angled. Does this have any discontinuities? Yes. Every integer here, every endpoint causes us to have to jump up, and so the left and the right hand limits at each of these endpoints would not match. So we have some discontinuities. Are they removable or non-removable? In this case, they would be non-removable because of those jumps. So non-removable discontinuities, and they are occurring at each of those endpoints which are at the integers. Okay? Next example here, we have that asymptote. So there's a discontinuity there because I have to jump over that asymptote to finish drawing my graph. Is an asymptote removable or non-removable? It's non-removable because I can't fix it by just filling in a hole. So we have a non-removable discontinuity at 2. Okay, the next one here is that little tiny hole. So we have to jump over that hole. Is that removable or non-removable? In this case, it's removable. Discontinuity at -1. And it is removable because you could just fill in that little hole and fix the problem. And lastly, we have that hole with a separate dot. That is also removable because you could redefine the function by just moving that dot down to fill that hole. But if we don't do that, then it's a removable discontinuity at x equals to c. So we really like continuous functions, and we're going to be using them quite a bit. So let's explore other ways you can get continuous functions. If you have a real number b, any constant, and f and g are continuous functions, then multiplying your function by a constant still keeps it continuous. Adding or subtracting continuous functions still keeps it continuous. Multiplying or dividing continuous functions still keeps it continuous. Also, every polynomial function is continuous. Every rational function is continuous, and rational means a polynomial divided by a polynomial, so those fractions. Every radical function is continuous, and every trigonometric function is continuous. So those are good things to know. What we're going to do in this next set of problems is find the x values, if any, at which f is not continuous, and then we're going to classify that discontinuity as removable or non-removable, and if it is removable, we're going to redefine our function to remove the discontinuity. Now, things to look out for where you might have discontinuities. Remember that you're going to have discontinuities anywhere that you have holes in your graph, anywhere that you have jumps or asymptotes. And the kinds of functions that sort of lend themselves to those things would be jumps, which might happen with our greatest integer functions, which are those step functions, or our absolute value over a function like our Heaviside functions that we did earlier today, or piecewise functions. All of those sometimes tend to have jumps in them. You might have some asymptotes if you're dealing with a fraction that could potentially be divided by 0. And that's what we have here. We don't have any piecewise greatest integers or absolute values, but we do have a fraction. So this could be bad news if the denominator ever became 0. So that's what you need to look at. So is it possible for x squared plus 1 to ever equal 0? Well, if you tried to solve this, then you'd be trying to take the square root of a negative number, and we're only dealing with real numbers in this course, so that doesn't have any real solutions. Therefore, it's not possible to divide by 0 in this problem, so that means we don't have any bad points that might cause us to have an asymptote. So there are no asymptotes for this graph, no vertical asymptotes. So if there's no vertical asymptotes, then we don't have any of those kinds of discontinuities, which means every x here is okay. How do you show where it's continuous? Well, we would say it's continuous everywhere, since there were no bad points. And if we wanted to write it using an interval, that means it's continuous from -infinity up to +infinity. Now the next example is very similar. Again, we don't have a piecewise function, any greatest integer functions, any absolute values to worry about, but we do have a fraction that could potentially cause us to divide by 0. And here you can see that that might happen if x is 1. So if x is 1, that's going to result in a vertical asymptote, which would be a discontinuity. And since it's an asymptote that we're talking about, That is a non-removable discontinuity at +1. So where is this continuous? It's continuous everywhere else. So if we wanted to write out the intervals where it was continuous, that would be -infinity up to 1, union 1 to infinity. Okay, if we try the next example, we have f of x equals x minus 3 over x squared minus 9. Again, we don't have any absolute values, any greatest integer functions, any piecewise functions, but we do have that fraction, and that denominator could become 0, potentially. Notice that it is a difference of squares, so if I factor the bottom, there's two things happening, and this is important. On the top you have an x minus 3, and on the bottom you have an x minus 3. Those want to cancel each other out, leaving you with this more simplified function 1 over x plus 3. Does that mean that nothing is happening at +3? That's not true, right? What is happening at +3? You're not getting an asymptote, but you are getting a whole. So when you get a factor like this that cancels out on top and bottom, that's going to result in a whole in your graph. What's happening with this other factor still left in the denominator, so that would be at -3, well, that is still an asymptote because it was left over. So we have two different issues. The asymptote is a non-removable discontinuity. The whole is a removable discontinuity. So for the removable one only, how could we fix this so that it wasn't a discontinuity at 3? Well, what we're going to do is we're going to redefine our function to take out the whole. Well, let me reword that. Instead of taking out the whole, let me reword it and say to fill the whole. So let's think about how we could do that. Where is the whole happening at? We know it's happening when x is 3, but what's the y value of this whole? Well, to find the y value of the whole, you have to remember that this function is really acting just like this more simplified 1 over x plus 3. And what is this simplified function doing at x equals to 3? If you were to plug in x equals to 3, that's going to give you 1/6. So this whole is at 3 for x and 1/6 for y. So what we need to do is fill the hole and put a black dot right at that hole. So here's how we do it. I'm going to be a little fancy here. I'm going to create a piecewise function. I'm going to say that this function is exactly like this more simplified 1 over x plus 3 everywhere except at 3. And what I wanted to do right at 3 is equal to 1/6. Okay? Let's take a look at the next example. We have the absolute value of x minus 3 over x minus 3, and that you should recognize by now as one of those Heaviside functions. Because of that minus 3 in there, that means we are shifting this to the right 3 units. So let's draw a picture of this. Instead of having those open circles at 0, we're going to have those open circles at 3, and my step, it goes to the right at a height of 1 to the right of 3, and it goes to a height of -1 to the left of 3. So there's my graph, and you can just see from this graph that I have a jump right at 3. So we have that jump discontinuity, which is non-removable at x equals to 3. Everywhere else is okay. Alright? Alright, let's try a piecewise function now. We want to find out where this is continuous or not, and if it has any discontinuities. So the first thing that you want to consider when you're talking about one of these piecewise functions is looking at the two individual rules themselves. -2x is a nice linear polynomial, and we know that all polynomials are continuous. And the second rule down here is a quadratic polynomial, so it is also continuous. So these are always continuous. The only troublesome point would be where we join these two guys together. And that's right at this breaking point right here. So at 2, there is a potential for a jump. So we have to examine whether or not we have a jump at 2. Everywhere else is going to be just fine because we will be on continuous functions. It's just where we join these two pieces together, whether or not they line up or not. So all you really have to look at for these piecewise functions are these breaking points over here. So here's how we're going to do it. A jump occurs because your left-hand limit is not equal to your right-hand limit. So we need to actually calculate algebraically what our left-hand and our right-hand limits are. So this is the kind of work that I would want to see when you're doing these problems. Let's find the left-hand limit first. So that would be the left-hand limit as we approach 2. And if we're coming from the left side of 2, that means x is slightly smaller than 2. That means we're on this line. So we should be using the formula negative 2x. And since that's a nice linear function, if I just plug in 2, that should tell me what my limit is. So this left-hand limit is negative 4. Now let's find the right-hand limit. So we're going to take the limit as I approach 2 from the right-hand side, so slightly bigger than 2, which means we're now on the quadratic function. And again, that's a nice polynomial, so to get the limit itself, you just plug in 2. 2 squared is 4. 4 minus 8 is negative 4 plus 1, so this is negative 3. Based on the left-hand and the right-hand limits, that should tell you whether or not the two-sided limit exists or not. So what's the two-sided limit of f of x? Well, since the left-hand limit was negative 4 and the right-hand limit was negative 3, those don't match. The two-sided limit is d and e. And that's because the left-hand limit does not equal to the right-hand limit. So what does that say about continuity? Because this limit doesn't exist, that implies that f is discontinuous at x equals to 2 because there is a jump. Okay? It's continuous everywhere else except at that breaking point because that's where we have our jump. Alright, let's try this again. This time we have a piecewise function that involves a trig function, tangent of pi x over 4, for the absolute value of x's less than 1. Now that's just a fancy way of saying that these are all the x's between negative 1 and positive 1. Outside of that, absolute value of x greater than or equal to 1, our function is defined to be x. So absolute value of x greater than or equal to 1 means either x is less than or equal to negative 1 or x is greater than or equal to positive 1. So we're covering all the values of x here in the middle and in the two tails or the two extremes. So if we look at our two individual functions, first of all, tangent is a trigonometric function. That makes it continuous. And x is a polynomial. So both of these are continuous everywhere, except potentially at the breaking points. And what are my two breaking points? Well, if you look at your inequalities that we have here, we're looking at x between negative 1 and 1 for the top rule and x less than negative 1 or greater than 1 for the bottom rule. So negative 1 and positive 1 are the two different places where these are joining together. So we have to look at plus and minus 1 and see what's happening. So we want to do the same argument that we did on this last problem, but we actually need to do it twice. We need to find the left-hand limit and the right-hand limit at 1, and then we need to find the left-hand limit and right-hand limit at negative 1. and see if they match. And if they don't match, that means the limit doesn't exist, so we have a discontinuity. If they do match, then that means we don't have a jump, so it is continuous. So let's start with x equals to 1. If I want the left-hand limit as I approach 1 from the left-hand side, when I'm coming from the left-hand side of 1, that means I'm slightly smaller than 1. That's what this inequality is right here. Slightly less than 1, so I need to be using this tangent function. And tangent or all trig functions are normally nice continuous functions, so we should just be able to plug in 1 into that to get our answer. So if I plug in 1, I'm going to get the tangent of pi over 4. You should know that that's root 2 over 2 divided by root 2 over 2, or just 1. Now let's do the right-hand limit. So if I take the right-hand limit of 1, so I'm coming from the right side of 1, so slightly greater than 1. That's what this inequality is. So I should be using this rule. And that's a nice line, so I can just plug in 1, and I'm going to get 1 back. So these match, which means it's continuous at 1. So we don't have a jump happening at 1 because the left and the rights matched. They lined right up. Let's see what happens at negative 1. So if we want the left-hand limit as I approach negative 1, so I need to be smaller or less than negative 1. Here's less than negative 1, so I need to use the x rule. And if I plug negative 1 into that, I'm going to get negative 1 back. So that's our left-hand limit. Now let's do our right-hand limit as I approach negative 1. So now I need to be greater than negative 1. That's what this one says. So we want to use our tangent function. If I plug in negative 1 into that, this would be tangent of negative pi over 4, which is quadrant 4, and in quadrant 4, tangent is negative 1. So again, these match, so we are continuous. So we were continuous everywhere already except potentially at these breaking points, and we just showed that at the breaking points there wasn't a jump, so they're not a problem either. That means that this function is continuous everywhere, and we have no discontinuities at all. Okay? Alright, let's take a look at the next example here. Here we just want to look at these graphs and state the interval of continuity. So where is this a nice, smooth, connected graph without any of those troublesome behaviors like holes, jumps, or asymptotes? Well, this graph starts at negative 3. It actually hits it, so I'm going to use a bracket there, and then it continues nice and smoothly to the right as I go to infinity, and there's no unusual behavior. So it's continuous on the interval negative 3 to infinity. For this second graph here, this graph appears to have a vertical asymptote at 0. So it's sort of starting at 0 and then going off towards infinity. But because it's never actually hitting 0, it's just approaching it through that asymptote, we don't want to include 0 in our endpoint. So use a parenthesis. Now this next example is a really good example, and you'll probably see these on homeworks and tests and exams. So make sure that you're able to do these. This problem gives us a piecewise function. X is our input value, and A is sort of this mysterious constant that we don't know. And what we're trying to figure out is what should this value of A be so that this piecewise function is continuous. Now remember, with piecewise functions, you potentially have a jump in your graph that could lead to a discontinuity. So that's what we're going to try and prevent from happening. So in order to find out where this function is continuous, let's go to the definition of continuity as a place to start. And by the definition of a continuity, it says that the limit as you approach A of f of x needs to equal f of a. So let's think about this a little bit. What's our a? We don't know. We're trying to figure out what this a should be. But we have this function that's defined to be this fraction everywhere except at a. And then right at a, it's equal to 8. So this would be like something doing who knows what. We don't know necessarily what this is going to look like because we don't know A. There's a little place where we're leaving out right at A, and then at A itself, this is equal to 8. So you have a graph that looks something kind of like this. Now we want to pick the right value of A so that this hole gets filled in. So we need to find first this limit, and then we need to find this height here, which we actually already know is 8, and we want to set them equal to each other to force this hole to be filled. So we already know what the function is supposed to be at A. That's what this is. When x is A, the function is 8. So I already know what I want that little black dot to be. It's 8. But now we need to figure out what this limit is over here. So we're going to find this limit by using our rule. Limits look at what happens to the function near A. Not right at A, but near A. And if we're not right at A, then we're on this fraction over here. So you want to be using this x squared minus a squared over x minus a. Now if you were to plug in a into that, you'd get a squared minus a squared, which is 0, over a minus a, which is 0. So it's an indeterminate form. So right now we can't figure out what this limit is. But we can be a little bit clever, and we can notice that that numerator does factor into a difference of squares. So if I factor it, and then notice that the x minus a on top cancels with the x minus a on the bottom, then that leaves me with just x plus a, which I can then easily plug a into and get 2a. So the limit is going to be 2 times whatever a happens to be. And what do we want that limit to equal? Well, remember, we need it to equal that little black dot so that these two overlap and they don't have a jump or a hole. So we have to force 2a, which is what this limit is down here, to equal this height up here at 8. And the only value of a that's going to make that happen is a equal to 4. So if a equals to 4, then f will be continuous. Okay? And we're going to finish up today with one last theorem, a very important theorem that's used in a lot of proofs, and it's called the intermediate value theorem. It requires that you start with a function f that is continuous. It has to be continuous on a closed interval a to b. The a and the b are the x values, and we're going to pick any number k that you want that's between f of a and f of b. So, for example, here's a, and here's b, here's f of a, here's f of b. So you get to pick any k that's between these two heights. So here I'm just picking some k in the middle. What the intermediate value theorem says is since f is continuous, there is no way that the graph of f can go from f of a down to f of b without crossing this line k at least once. And in this example, for this function, it actually hits 3 different times. So there's at least one of these c's, there's a c1, c2, and c3 in this example, where the function takes on the height of k. So the intermediate value theorem guarantees that one of these c's has to exist between a and b so that f of c equals that height k. Now, what could go wrong if your function is not continuous? Imagine this example over here. Here we have a function. This is f of a, and this is f of b, and then we have this k down here. And notice that this function goes down and then jumps down here and jumps right over that height k. So this definitely does not hit that height k at all, and the sole reason why it does not is because it wasn't continuous and it had that jump in there. So it's really, really important that your function be continuous. Now, one of the most common applications of this intermediate value theorem is in finding zeros. And we're going to use that to solve the next couple of problems. But the idea is that you're going to have a continuous function where you know that it's negative at one point and positive at another point. And the only way it can go from this negative to this positive is if it hits 0 at least once. Now in this example here it hit just once, but maybe this hits more than once. So this would have 3 different zeros between A and B. Okay? So the intermediate value theorem guarantees that there has to be 1 0 at least between A and B. So let's prove an example like this. Use the intermediate value theorem to show that f of x equals x cubed plus 2x minus 1 has a 0 in the interval 0 to 1. So 0 to 1, that's your A and your B, and my function is this cubic polynomial. Now before you can use the intermediate value theorem, you have to justify the fact that you have a continuous function. Otherwise the intermediate value theorem may not be true. So if we are letting our f of x be this cubic function right here, is that continuous? Yes, f is continuous because it is a polynomial, and that's a theorem. You can just state that. All polynomials, all rational functions, all radical functions, and all trigonometric functions are continuous. So now that we know that f is continuous, let's look at that f of a and that f of b, which in this problem is f of 0 and f of 1. So to find f of 0, just go to your function and plug in 0 for these x's. So 0 cubed plus 2 times 0 minus 1 is just negative 1. And if I plug in 1, 1 cubed is 1, plus 2 is 3, 3 minus 1 is 2. Now let's just visualize this a little bit. This is saying that when x is 0, y is negative 1, and when x is 1, y is 2. And this is a continuous function. So how is it possible for this graph to go from this negative value, whoops, sorry about that, from this negative up to this positive without crossing at least once? It has to. That's what the intermediate value theorem says. The intermediate value theorem guarantees that there exists, that's what this backward E means, there exists at least one value C between 0 and 1. So we have to be between 0 and 1. There has to be at least one of these C's such that f of C is equal to 0. And if f of C is equal to 0, then C is the 0 that we're looking for between 0 and 1. This is actually what your calculator does in a very quick process. It narrows down intervals until it can get as close to that C as possible. So it might start by zooming in and finding that there has to be a 0 between 0 and 1, and then it'll shrink down this interval and know that it's between, these two values, and keep on shrinking, finding positives and negatives until it gets to the desired accuracy that you're looking for. Let's try this one more time with one last example. This time we want to use the intermediate value theorem to prove that square root of 3 is between 1 and 2. So you all can take square root of 3 and punch it into your calculator and get a decimal, but that's just an approximation to what the square root of 3 actually is. What we're going to prove using this intermediate value theorem is that it has to be somewhere between 1 and 2. And then if you wanted, you could go into further detail and shrink down that interval and get more and more accuracy. But we're just going to prove that it's between 1 and 2. So the trickiest part about this problem is figuring out what function to use. If you're going to use the intermediate value theorem, then you need some f of x that's continuous to work with. So here's what we're going to do. We're going to try to make this problem become just like the last example. We're going to try and find a function that has square root of 3 as a 0. You have to think backwards on this. If you were to set some function equal to 0 and solve it, what function would you need over here in order to have square root of 3 showing up? And the easiest answer that you could use would be x squared minus 3. You wouldn't want to use x minus square root of 3 because that presumes that you know what square root of 3 already is. We know what 3 is, but we don't know what square root of 3 is. So you need to kind of go back and use a quadratic. If I were to solve this, I actually am going to get two solutions, plus or minus root 3. But we're only going to be interested in the positive one. So we're going to let our function f of x be x squared minus 3, and we're going to prove that it has a 0 between 1 and 2. So to prove that something has a 0 using the intermediate value theorem, first thing we have to do is show that this f is continuous. And why is x squared minus 3 continuous? Because it is a polynomial. It's just a quadratic function. So we know that that's true. Okay, once you've shown that your function that you're working with is continuous, then you need to look at f of a and f of b. And here our a is 1, so we want to look at f of 1, and our b is 2, so we want to look at f of b, which would be f of 2. And we're going to plug in 1 into this x squared minus 3 function. 1 squared minus 3 is negative 2. And if I plug in 2, 2 squared minus 3 is 4 minus 3, or 1. So to visualize this, when x is 1, y is negative 2, and when x is 2, y is 1. We know we have a continuous function, so the intermediate value theorem guarantees that I have to cross at 0 at least once, because 0 is between a negative and a positive. So the intermediate value theorem guarantees that there exists at least one c between 1 and 2 such that f of c is equal to 0. And what does f of c equaling 0 imply? Well, since our function is x squared minus 3, that would be c squared minus 3, and setting that to 0 would give us as a solution that plus or minus root 3. Since our c is forced to be between 1 and 2, that's the only proof that we've shown so far, is that it's only true between 1 and 2, we can only use the positive value. So what we've just shown is that the square root of 3 has to be in this interval 1 to 2, because that's where I had to have crossed 0. So this is our c, and that's our root 3, which implies it's between 1 and 2. So there's our proof. Alright, that concludes our lecture on one-sided limits and continuity. Good luck!